I want everybody to remember that isotope is dangerous. 4,000 volt or 6,000 volt isotope can generate some very nasty X-rays. So you got to be really careful with this. And when you get up to 60,000 volt isotope, you're in really super high X-ray type stuff when those beta particles hit metal objects and X-ray comes out. So let's talk about Fe55. Since most of you want to build something that's doable, Fe55 is about as close as you can get to a standard microwave magnetron. And if you're looking for something that's a lightweight device that puts out a lot of power, then Fe55 is a good choice, because if you get an isotope like strontium-90 that is much higher in voltage, you need bigger, heavier magnets to make the confinement ring work, and the weight ratio to power ratio goes up. Strontium-90 is fine for something that's going to stay on the ground, but Fe55 is a better choice for something if you want to fly around in it, and that type of a thing. If you were driving a truck, strontium-90 would be fine, but if you want to fly in an aircraft, you want something that uses lightweight magnets and makes the device light. And Fe55, you can add more isotope. The cost ratio changes quite a bit in that case, as far as between Fe55 and strontium-90 when you look at it from a power point. That strontium-90 gives you a lot more power for the money than Fe55 does. So there's a lot of different trade-offs with working with isotope as far as what you want to do with it. But weight-wise, Fe55 will give you as much energy. You can make it give you as much energy as what strontium-90 will by just upping how hot it is, put it in the reactor and, make it have more output and that type of thing. So these isotopes, there's a few of them. Once you get above that 60,000 volt level with isotopes, you wind up that you have to put some kind of mediator, something in there that's going to slow the electrons down. And anytime you do that, you generate heat. If you're lucky, you can put something in there that will divide the energy up, produce more electrons. Like if you put diamond inside mix the Fe55 with diamond, that when it hit diamond, it produces more electrons and the energy is divided and that kind of thing, that you can get more of an electron field. You're also trying to do impedance matching with this isotope. A lot of people don't realize that when you're trying to produce the maximum amount of energy with the isotope, that you're actually doing an impedance matching between the resonators and the isotope that's emitting the electrons or beta particles. Or in the case of a different type of isotope that may produce alpha particles, then you're trying to do the same thing with that. You're trying to do an impedance match between the resonators and the isotope. And a lot of times this isn't possible, depending on how much power you're trying to do. You may not get a perfect impedance match, but that's what you're trying to achieve. And of course, over time, the isotope will have some kind of a half-life. If it's Fe55, it'll be 3 years. If it's strontium-90, it'll be 28 years, and that impedance matching will change over that time because of the amount of electrons that are in the field that are rotating. A lot of people don't seem to realize this, but this does happen. So when you're picking isotope and using it, you have to sort of take all of this into consideration when you're trying to build one of these devices. Let's cover isotope anomalies. There's some anomalies about isotope that a lot of people don't talk about, and some people don't even know about these things. Isotopes are very noisy because of how they decay, and using isotopes in vacuum tubes, not magnetrons, vacuum tubes that actually amplify signals, they do not do a good job at all. They mostly produce noise. And the other thing about isotope is the fact that isotope output, the amount of decay that happens over time, can vary as much as 50% in some cases. And some of this decay depends on how many sunspots the sun's putting out at a particular time. Sunspots can change the amount of decay in an isotope. Nobody seems to know why. There's some theories about it, but it does change, and it will change from day to day somewhat. The isotope, nobody knows why this happens other than it does happen. So from the perspective of using it on a regular vacuum tube, that people have tried it and it doesn't work well. The sunspots, nobody knows the answer. And it does produce noise, but in a magnetron, because of it producing microwave, the tube doesn't care about noise. That's not what it's designed to do. It's designed to oscillate. So noise really makes no difference in a magnetron as far as how it's going to operate. Now, the change in current in the magnetron will change the magnetron frequency somewhat. It depends on how much it changed and how tightly coupled the magnetron is with the resonators and things like that. So even though there may be a large amount of current change, that doesn't mean the magnetron frequency is going to drift all over the place. It may drift a few hundred kilocycles, or it may drift something a little larger than that, but some giant drift change in the magnetron, that's not likely to happen. All right, let's take a look at how this electrically looks to the magnetron with the isotope. The isotope looks like a constant voltage, constant current power supply that develops a rotating electron cloud field, depending on how many matching resonators you have inside in the magnetron. So even though the isotope changes its constant current level from day to day, it's slow enough that you can consider it constant current. In that case, it's not something that does instantaneous changes. It may go up or down in several hours, but it's not something that moves so fast that it changes how the actual resonators work. Magnetrons stay pretty well locked to frequency, even if there's a fair amount of current change within the device. So from this perspective, once you get the magnetron running, okay, which is a little different than a standard magnetron to get it running. Once you get it running, it will continue to act like a normal power supply, and it might be harder to shut off than you think once it gets going. So the constant, like I said, the isotope's really a device that it's emitting either alpha particles or it's emitting beta particles, electrons, and the only difference is it doesn't have a power supply hooked to it. It just doesn't, and you need the spark gap across the two, the anode and the cathode side of it, because the electrons that fall back to the isotope at some point need a way to discharge. Otherwise you wind up building up fields on both ends of it, and it could stop, but it might not. So that's pretty much it for isotope as far as how it works electrically. Watch the next video on isotopes are green energy. It's very informative about nuclear waste